So, can you, well, I mean, I know most of you. So, what are the ways you have used your computer for doing math in the last year, for example? Can you have some ideas? Not the one you're thinking about. Yeah.
The only one I've done is typing stuff up in LaTeX.
Okay. Okay. This is one way of using computers and typing later. Okay. Yeah.
I run simulations of like models and
Okay. Simulations. Any ideas? Yeah.
I run Mathematica.
Okay.
And Sayantan.
To do what exactly?
Just some stuff like Newton's method and numerical analysis.
Okay.
In grad numerical analysis, I did something similar, like with the optimization of certain algorithms.
Anything else? No? Okay. Well, that's already something. Yeah. What did you say?
Symbolic calculations.
Symbolic calculations. So let's write them.
Thank you.
Yes.
Category theory using Haskell.
I don't know if I should write it here or yeah.
It's close enough.
Okay. Let's keep this in mind, but I don't want to write it. Okay. I had three categories, and this doesn't fall in any of them. Yeah.
I use integralcalculator.com when I'm tired. No, but that's a good one.
Okay, so actually mathematicians have been using computers for centuries. Okay, and I really mean centuries, not just centuries, because so already in the 16th and 16th century, research mathematicians were using human calculators, human computers, to, for example, to create tables of prime numbers, tables of logarithms, tables of other transcendental functions. Okay, and this is something we can write next to simulations and numerical analysis and these things. Okay, tables, because what all these things have in common is that they do some scientific computing. Okay. So this is the scientific computing, in the sense that we want to compute with all the accuracy you can some numerical values. Okay. I can call this thing like accessory duties, accessory tasks to mathematics, but they are also very important because, for example, well, I mean, Google is really useful also for research mathematicians. So this is probably the first thing people did with computers, okay, scientific computing. And then people started using also computers for doing symbolic calculations, okay, so these things. So they can use these, I mean, general purpose languages, but they can also use computer algebra systems. Okay, so far we have seen that computers are used to do computations. Okay, so actual numerical computations or abstract computations, but in both cases these are computations. And today we want to show you that there's another thing we can do with computers, and this is and that is also a very important part of the mathematician's job. And so mathematicians, of course, do some computation. Some mathematicians do computations, okay, And these are important for many branches of mathematics, but what every mathematician does is they prove things, okay? And actually, computers can also help with proofs, okay? So, the new thing we're gonna talk about is proof formalization. Okay? Well, do you know what a proof is? Are you all familiar with proofs? Have you all taken like at least discrete math? Yes? Okay, perfect. Then you have all done proofs, and then you know that a proof is like a sequence of arguments that allow us to go from some assumptions through some logical steps to the conclusions. Okay, so if we want computers to help with proofs, then we need the computers to be able to first to know the actions we are using. Okay, but this is just data. Okay, and computers can manage data. And then second, we need the computers to be able to check that the steps we are following, we are performing, are correct. So these logical steps are correct. Okay, but computers are also good with logic. So they have all the ingredients. So and this is exactly what proof assistants do, okay? They are going to do these two things. So now, what's the downside of these? Okay, why aren't we all using computers for that? The reason is that if you are familiar with programming, you know that when you talk to a computer, you need to do that in a very specific way, okay? They are very strict with the language they can understand, okay? And so you have probably in your discrete math class, for example, you have probably had feedback from your professor saying you need to be more rigorous when you write proofs. Okay, well here this is pushed to the limit. You have to be extremely rigorous when you write proofs for computers. Okay. Then yeah, proof formalization is just a translation of proofs into a language that computers can understand. Okay, and this is gonna be, we'll do some practice now. You will see that this can take a long time, but the good point is that well, it can guarantee that your proof is correct. Okay, you can check that and be 100% sure that the homework you are submitting is correct. Okay. And it has a lot of other applications. So, for example, some applications of proof formalization are well for research mathematicians. Of course, we can check that the proofs are correct. This is the first thing, but not just for your homework, but for research level mathematics. And you may think, well, I mean, professional people probably don't need a computer to tell them that the proof is correct, but they do. Okay, and they probably need that more than you do, because there are proofs that are crazily difficult and impossible to understand. Maybe you have heard about something called ABC conjecture. This is a conjecture, old conjecture, and there's someone in Japan who probably more than 10 years ago claimed that he had proved this conjecture, and yeah, for more than 10 years, people are still deciding if he proved it or not, because they are not able to understand the proof. Okay, it seems that it has some gaps, but some people say, well, the gaps are too big and they will never be able to complete the proof. He says they are not understanding my math because yeah, it's too hard, but this problem would be solved if someone formalized it, because yeah, the computer will tell you it's correct or it's not correct. Okay, and there are many other examples of this. Then another related field of application is for collaboration of research mathematicians, because when we collaborate with other mathematicians, we need to trust these people, because these people are going to prove things that we are going to use. So either we trust them and we say, well, they are very strong, so we will believe that, or we have to double check this. Actually, we should double check it. But So there is a trust component, which is very important in collaboration. And if you use formalization, then, well, the other person will write the proofs, and then if the computer checks that the proof is true, you don't even have to double check that. Okay? So this makes possible, for example, large-scale collaboration. Usually in math, you collaborate with one more person, or maybe 2, 3, 4, but usually no more than that. Okay? In computer science, they are writing programs in teams that are very, very big. So mathematics could go in this direction if we had something to check that proofs are correct. Okay? Another thing where we can apply this, and then this is maybe closer to your interests, is for teaching and studying. Okay, because there are some people trying to. Okay, of course, you're gonna see that the language we need to use to formalize these proofs is not very clear. I mean, it's far from being clear. But it's possible to, so there are people working on making it understandable. So this is an example. This is under development, okay? So there are no many more examples, but this is an example of theorem from topology. Okay? I will not go into the details of the math behind this theorem, but actually this theorem and its proof has been automatically generated from the lean code of the proof. Okay? And so this can be used like a textbook. And the advantage of this textbook is that if you don't understand one step, this is like the high-level proof. This is what, if I had to teach this theorem in class, I would write this proof, okay? But if you don't understand one step, you can expand. So this is what Sayantan has just done. He has expanded the first line because there was something else behind these, okay? And if I don't understand, for example, these bar, well, because yeah, I mean, you can expand and you can see all the details. Okay, so you can see the details as in depth as you want. Can you please click on expandable? And now this takes a moment, but now can you like go up and down just to show what the full proof with all the details would takes us to? Okay, so yeah, every time you are confused with one single step in a proof, you could just expand and you get the details. Okay? And something else that is connected with proof formalization is AI. Okay. So far I'm talking about proofs, human written proofs that we want to formalize. So we want to write them in a language that computers can understand. Okay? But the next step is, well, once computers have this language, the next step is, can they write their own proofs? Okay, and there are also projects working on these. And in Google DeepMind, they have a project and they have a generative AI that is already able to prove some international mathematics Olympiad problems on its own. Okay, so produce proofs that can be checked. And these are not easy problems in general. Okay. So yeah, these are just some of the applications. And well, today we would like you to practice some practice of proof formalization, specifically in Lean, which is probably the most commonly used system nowadays. There are a few others, but this is probably the most popular right now. Okay, so Sayantan will now give you a brief introduction to Lean, and then we'll go through the practice.
Yeah. So Lean is a functional programming language. It's like any other functional programming language in the sense that you can do normal functional programming things in it, like the first thing that you always do is do a hello world. I just did a hello world there. You can do eval hello world, and I am currently using an interactive mode of Lean, which is very useful for pure improving, as you will see. We're doing like normal stuff like adding 2 plus 2, which I'm checking the type of 2 plus 2, which it tells us that it's a natural number. So there's a type engine in it. And we can do an eval of 2 plus 2, and that comes out to be 4. So the Lean kernel actually knows how to add some very default types like integers in this example. We can define functions, like let's define f of x to be x plus 3, and then we can evaluate these functions. And as you can see, the layout of this function, of this language, the syntax is very functional, right? If you have ever done like, he said Haskell, it has a very similar syntax.
Yeah.
Yeah? We are applying 5 to the function f and we're getting a. And yeah, it's checking f is just a function from natural to natural numbers. All right. Here I have defined a factorial function, which we are going to use for our proof. And I defined it using the fact that natural numbers are defined inductively. So I defined that factorial for 0 should be 1. And for any successive numbers, it should be factorial of n times its successor, which is how we define factorials in general, right? And Lean is able to figure out the factorial for 5 from this definition. Now we're gonna actually do a proof.
Yes, so we'll prove a very simple, well, we'll have the proof of a very simple theorem, okay? So we are gonna prove that if n and p are natural numbers, and p is actually a prime number, then if p is greater than n, then p doesn't divide n factorial. Okay, this bar means divide, so cross bar means doesn't divide n factorial. Okay, so this is a simple theorem, right? If I had to prove this in class, I would say, well, let's take n, okay, some natural number, and p, and then by contradiction, so assume by contradiction that p divides n factorial. But then n factorial is equal to n times n minus 1 times n minus 2, and so on until I arrive to 1. Okay? So if now p is prime and p divides this product, so since p is prime, then either p divides n or p divides n minus 1, okay, or p divides n minus 2, okay, or p divides 1, okay, which is possible, but yeah. But then, if p divides n, this means that p is smaller than n, smaller or equal than n. Okay? If p divides n minus 1, this implies that p is smaller or equal than n minus 1. And anyway, there's only one situation that works, maybe only one situation that works, but anyway, we will need p to be smaller or equal than n. Okay? Then p is smaller or equal than n, but this is a contradiction because we were assuming that p is greater than n. So p was greater than n by assumption, so this is a contradiction. Okay, so the statement is proof. This is how the proof will be in regular English. Okay, mathematical English. So now the proof in here.
Yeah, so the first thing that we should do is try to translate the statement of the theorem into mean. So first of all, let's say that P and N are two natural numbers. We do that like this. Then we say that P is actually prime. Nat.prime is the prime type in mean. You can see that there are curly braces around this and parentheses around this. There's a slight difference. The curly braces are implicit types and parentheses are explicit types, so we can give names to these things, right? So this property has a name prime P that we're going to use inside the proof. Similarly, we have the other statements as different named variables, like PGTN is just standing for P greater than N. And then we have what we want to prove, which is that not P divides factorial N, which means P does not divide factorial N. It's just the way we write it in mean. Okay, now we actually start the proof. And most of the proofs start, at least most of the complicated proofs start by saying a by. And then we go to the next line. Okay. Now, this exact proof that Mario did here is not as easy to translate in mean as it is in English, because the main problem is that here we use the fact that n times n minus 1 times 1, we know how to work with a product of finitely many numbers, right? We don't actually go into how we work with them, we just implicitly understand how to work with them, but mean doesn't. There is a way to work with this exact proof here using fin sets in mean. We have implemented fin sets in mean, but that will be much more complicated. So we will use the proof, the same logic of this proof, but we will use a different flow that is much easier to understand. So what we do first is, so we're going to follow these steps that we have outlined here. So first we will use a contradiction. So assume that P does actually divide n factorial, and then we will derive a false statement that basically means a contradiction. So we do the by contra. So if you look at the right side, you will see that there is now this variable which has P divides factorial n. It wasn't there before, right? It was introduced by the by contra. And you will use that to prove false. Now the goal state is now false.
So maybe say this part tells you the current state of your proof. So it tells you what are your objects, what are your hypotheses, and what is your goal. Okay, and your goal is can you move to the beginning of the line, please?
Yeah.
Yeah. So your goal originally was to prove that it's not true that P divides factorial of n. After you apply contradiction, you have one new hypothesis, that is the hypothesis this, and the new goal is to prove false. Okay? Sorry.
Yeah, now that we have that, we will use induction to do this proof. We will do induction over n with m as a variable and the induction hypothesis IH. So now we will see that we have introduced a natural number m and an induction hypothesis, which is written there and also on the board. But we will focus on the base step of this induction because we don't really want to waste a lot of time doing the whole of the proof. So what is the base state? The base state is the case 0. And then we want to basically prove that P divides the factorial of 0, right? So to do that, we need to know what the factorial of 0 is. And for that, we use the unfold tactic. Oh yeah, I haven't formally defined what a tactic is. So a tactic is it's a monad in functional programming, but what you need to understand is that it takes a proof state and transforms into another proof state. Right? So we have the state of this proof here, which has all of these variables, and when I do unfold the definition of factorial at this is the property of p divides factorial 0, we will have a new proof state, right? Which rewrites the fact 0 by a 1. It uses the definition of the factorial function. Okay?
Yep.
So as you see, it was fact 0, now it's 1. We use the fact that factorial of 0 is 1. Yeah, so we now have a new proof state because we applied that tactic. And by the way, the by contra and induction were also tactics. Now we use the applied tactic. So we look at step 4. So we need to prove that we want to prove that 1 is less than p. And for that, we apply this theorem, prime.1nt, which is proved inside the library of Lean, which is called mathlib. We use that at prime p. Now prime p is nat.prime p, which means that p is a prime. Right? We use the theorem that for every prime p, 1 is less than p on the fact that p is a prime. So that gives us the fact that p is greater than 1. Okay? So we had p is a prime. Now we have that p is greater than 1. Okay. Now we want to have a contradiction by showing that p is also less than or equal to 1. Okay, so we have a half tactic of p less than or equal to 1. This is basically a way to introduce something new that we want to prove. And now we have a new goal of showing that p is less than or equal to 1. Okay? And here we will use the theorem called LE of DVD, which means that division implies less than or equal to. Right? So we have p divides 1, which is the property this, and that should imply that p less than or equal to 1. And the theorem in Lean which says that is called LE of DVD. So we apply LE of DVD at this to get p less than or equal to 1 at this. And then since we have exactly what we want, p less than or equal to 1 as a variable, we just apply trivial on it, and that proves the goal. Now one thing here is that I am using trivial multiple times, so I am using that silly quotation, silly notation here. This just applies something however many times it needs to do to prove the goal. Okay, and now we have at prime p we have 1 less than p, and at p LE1 we have p less than or equal to 1, and those two together give us a contradiction. So Lean array is a tactic that looks at such things and gives us a contradiction. So we just use it and uphold this.
At what point do we start simping? See simp at there.
We can.
No, just keep going. Ignore me.
So, did you choose the theorem LE of DVD, or did Lean come up with it?
So the theorem LE of DVD is inside the mathlib, which is a library of.
Did you tell Lean to go to find that theorem?
Yes. Yes.
So you needed to know what was in the library.
Yeah. So I had to add all of the things in the library here manually, and
Is it like defined at the top where you had that?
Yes.
Yeah. Okay.
I had to import all of the stuff that I need.
Very nice.
Okay, yeah. Then we prove the rest of the theorem, but we're not going to do it here. This is just doing the inductive step, which is much more complicated. Let's not waste your time doing it. So we will just switch to doing the exercises, basically.
Yes. Basically, the search remaining time we have, that I thought would be 45 minutes, and actually it's less than 25.
Yep.
But you can stay more than you want to. So we are gonna go over some games. So there are